Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, and I'm up to problem 2.13. I'm going to do 2.13 and 2.14 in this video. So it's the 4th edition of the book. Problem 2.13 is asking us if the specific energy of the two-body problem is negative, show that M2 cannot move outside a sphere of radius mu divided by the magnitude of the specific energy centered at M1. So it's not a complicated setup. We have M1 and M2, and the equation for the energy between these 2 points is v squared over 2 minus mu over r, r being the distance between the two bodies. And yes, so it wants us to show that it can't, this is the maximum r when this is negative, right? So what I'm going to do, I'm going to rearrange this equation in terms of speed to get a value for speed, velocity, and then that will help us prove this. So we'll rearrange it, and v equals the square root of 2 upon the energy plus mu over r. This is the gravitational constant, mu. From looking at this equation, you can see that if this is negative, if the energy is negative, then mu over r has to be greater than that absolute value. Otherwise, this square would be a square root of a negative value, and our velocity would be negative, and that makes no sense. And that's the magnitude there. You can't have a negative velocity. So we can say that mu over r has to be greater than the absolute value of the energy. And then we can just rearrange that quite easy to say that mu over the specific energy is less than r. Right? Sorry, r has to be less than that, yeah. So that's that, yeah, no problem, pretty straightforward. Then on to 2.14 is asking, relative to a non-rotating Cartesian coordinate frame with the origin at the center of the Earth, a spacecraft is in, so that's Earth, and our spacecraft here is in rectilinear, has a rectilinear trajectory, so it's going either towards or away from the Earth, and it has a velocity of 2I plus 3J plus 4K, and it's at a distance r of 10,000 kilometers. And it says find the position vector r when the spacecraft comes to rest. So I assume it's going this way. It's not going to crash into the Earth. So we want to find this point here where v equals 0. And this question is actually on the chapter of energy, as is the last question. So we just use that equation again. First, we have to figure out what the energy is at 10,000. So we make r equal to 10,000 kilometers. We know mu is the gravitational constant for Earth. We know the velocity, that's just the magnitude of velocity squared, and we get a value for energy. And then we simply rearrange the equation with velocity set to 0. So it just becomes, and we want to find the radius, so it just becomes r equals negative mu over energy. So if we take r0, r1, if we put that in here and solve it, and then you will get, that will be your magnitude r. So we have that, and then the vector r equals the velocity unit vector times r1, because they're both in the same direction. The velocity and the radius are in the same direction, so that will give you your radius vector. And that's it. Yeah, the scripts will be, MATLAB script will be down in the description. If you have any questions, let me know. Or if you think I've made a mistake, let me know in the comments. Thank you. Goodbye.